The first ever image of dark matter was captured. The mysterious substance that makes up most of the cosmos but which has never been observed is known as dark matter. Scientists have never seen more than 80% of the universe as matter. Since the behavior of stars, planets, and galaxies simply wouldn't make sense without it, we can only believe that dark matter exists. But lately, researchers found the first ever image of dark matter. The earliest ever finding of dark matter was made by scientists using a fossil remnant from the Big Bang. The earliest detection of this unknown material that permeates the universe has been made by scientists in the vicinity of galaxies that existed about 12 billion years ago. So let's see what they have found. Let's start by defining dark matter. Dark matter is entirely undetectable. Since it doesn't emit any light or energy, ordinary sensors and detectors are unable to pick it up. Scientists believe that its composition must hold the key to understanding its cryptic nature. Baryons, a general term for subatomic particles including protons, neutrons, and electrons, make up visible matter, also known as baryonic matter. What dark matter is constituted of is a topic of conjecture among scientists. It might be made of baryons, but it might also be non-baryonic, which is made of many kinds of particles. However, how can we be certain that dark matter exists if we cannot see it? Gravity, a force that is proportional to an object's mass, is generated by objects constituted of matter, is the answer. Since the 1920s, astronomers have proposed that the cosmos must include more matter than what we can see, since the gravitational forces that seem to be in operation in the universe just seem stronger than the visible matter alone would account for. The closest thing that scientists could demonstrate dark matter was its gravitational effects. But now, researchers from the University of Waterloo in Ontario, Canada have something even better: a composite image that demonstrates galaxies are genuinely connected by dark matter. To prove the presence of dark matter, the researchers combined images taken over an extended period of time using a technique known as weak gravitational lensing. The composite was created using data from more than 23,000 galaxy pairings that are 4.5 billion light-years away. Even while we still don't know what this substance is made of, we can now clearly see that it exists between galaxies. At a time when other scientists are putting forth theories that do away entirely with the need for dark matter, the picture is undoubtedly a huge step towards legitimizing dark matter and dark energy. The recent observations contradict the notion that dark matter is clumpy. The results, which are attained through a partnership led by scientists from Nagoya University in Japan, imply that dark matter in the early cosmos is less clumpy than many other current cosmological models anticipate. If future research supports this hypothesis, it may alter our understanding of how galaxies develop and suggest that the fundamental laws regulating the universe may have been different when it was only 1.7 billion years old, 13.7 billion years ago. The cosmic microwave background, CMB, a type of leftover radiation from the Big Bang that had dispersed throughout the whole cosmos, is the key to mapping dark matter in the very early universe. Look at dark matter around distant galaxies. It was a crazy idea. No one realized we could do this. University of Tokyo professor Masami Ouchi said in a statement, "But after I gave a talk about a large distant galaxy sample, Hironao came to me and said it may be possible to look at dark matter around these galaxies with the CMB." Astronomers perceive other galaxies as they were when the observed light left them, because light takes a finite amount of time to travel from faraway objects to Earth. The further away a galaxy is from us, the longer it has taken for its light to reach us, and as a result, the further back in time we view it. As a result, the farthest galaxies are visible to us as they were billions of years ago in the early universe. It is even harder to observe dark matter. Around 85% of the universe's entire mass is made up of the enigmatic element known as dark matter. It doesn't interact with matter and light in the same way as regular matter, which is composed of protons and neutrons and make up stars, planets, and ourselves. Astronomers must rely on the gravitational interaction of dark matter in order to see it at all. The curvature of space-time, according to Einstein's theory of relativity, is caused by massive objects. An illustration used frequently is a stretched rubber sheet supporting balls of increasing mass. The sheet develops a larger dent as the mass increases. The extremeness of the space-time warping is also proportional to the size of the cosmic object. Space-time is bent by galaxies and other large massive things in a way that is similar to how a stone rolling across a stretched rubber sheet might wander from its intended course. Gravitational lensing, a result of this effect, causes a change in the location of the light source in the sky. Astronomers can analyze how light from a source behind a galaxy is altered as it passes the lensed galaxy, in order to study the distribution of dark matter in that galaxy. The distortion of light flowing through a lensed galaxy increases with the amount of dark matter it contains. But there are drawbacks to the method. As astronomers gaze deeper into the cosmos and farther back in time, the lensing effect becomes more subtle and challenging to see, and scientists need both a lot of background sources and a lot of early galaxies to spot lensing by dark matter. This is because the earliest and most distant galaxies are very faint. Due to this issue, the mapping of the distribution of dark matter has been restricted to galaxies that are 8 to 10 billion years old. But compared to galaxies, the CMB offers a more older light source. When the cosmos cooled down sufficiently for atoms to form, fewer free electrons were available to scatter photons, leading to the creation of the CMB, which cosmologists refer to as the last scattering. The universe abruptly ceased being opaque to light and started to become transparent to light because to the decrease in free electrons, which allowed photons to travel freely. The CMB can also be distorted by galaxies with dark matter owing to gravitational lensing, just like light from other far-off sources. According to a statement from Yuichi Hurricane, an assistant professor at the University of Tokyo, most researchers use source galaxies to measure dark matter distribution from the present to 8 billion years ago. However, we could look further back into the past, because we used the more distant CMB to measure dark matter. The scientists found dark matter as early as 1.7 billion years ago by combining lensing distortions of a broad sample of ancient galaxies with those of the CMB. And this old dark matter depicts a completely different view of the cosmos. For the first time, according to Hurricane, they were measuring dark matter from almost the first moments of the universe, 12 billion years ago. Things were very different. You see more galaxies that are in the process of formation than at the present. The first galaxy clusters are starting to form as well. These clusters may contain between 100 and 1,000 galaxies that are gravitationally coupled to substantial amounts of dark matter. The prospect that dark matter in the early cosmos is less clumpy than many existing models predict is one of the most important parts of the team's discoveries. For instance, the popular lambda CDM model predicts the minute variations in the CMB should have caused gravity to produce densely packed pockets of matter. In addition to producing dense pockets of dark matter, these fluctuations should eventually cause matter to collapse to create galaxies, stars, and planets. Our finding is still uncertain, Hurricane said, but if it is true, it would suggest that the entire model is flawed as you go further back in time. This is exciting, because if the result holds after the uncertainties are reduced, it could suggest an improvement of the model that may provide insight into the nature of dark matter itself. The team will keep gathering information to determine if the lambda CDM model agrees with observations of dark matter in the early cosmos or whether the model's underlying presumptions need to be changed. The Subaru Hyper Subprime Cam Survey, which examines data from a telescope in Hawaii, provided the information the scientists utilized to arrive at their conclusions. But because just a third of the data has been used so far, a more accurate picture of the distribution of dark matter may emerge if the remaining observations are taken into account. Data from the Legacy Survey of Space and Time, LSST, of the Vera C. Rubin Observatory are also anticipated by the team since they may enable them to examine dark matter much further in the past. LSST will allow us to observe half the sky, Hurricane said. I don't see any reason we couldn't see the dark matter distribution 13 billion years ago next. Because it does in mind, all of this research may prompt the question of whether this dark matter phenomenon is dangerous. Dark matter holds around 1/4 of the universe's mass. According to a recent study, there is a risk that one type of it could behave like tiny, fast-moving projectiles that could penetrate human flesh like bullets. Scary but intriguing. In fact, the authors of the study predicted that the dark matter impact would produce so much heat that a plasma plume that melts flesh would tunnel through body tissue. That hypothesis may seem absurd, but since dark matter cannot be directly observed, it is important to give it significant thought until it can be ruled out. What do you think about this intriguing entity that lurks throughout the universe?